The video provides a multiaxial introduction to the WinLife software. To do this, two non-proportional loads are to be applied to the link shown. A new WinLife project is created. Here, example 7. If finite element results are used in the calculation, the method is set to elastic notch stress. We will evaluate the multiaxial conditions according to cross-sectional planes, hence multiaxial. The stresses from the FE calculations are available in LST files. The number of load cases is 2. An existing SN curve for this example is loaded. The SN curve dialog box opens. The values shown here uniquely determine the SN curve. The SN curve is displayed. Two existing load time functions are loaded. We wish to plot these two functions graphically. A large number of load values are included here. The corresponding stresses are now shown following the loads. Optionally, the geometry file of the calculation model can be specified to display the model with results in the viewer. The stresses were exported from the FE program and are available in LST files. The two files are specified. The FE force used to perform the FE calculation is specified for the files. In this case, 100 newtons act on the component for both load cases. First, we carry out a rough analysis. This allows results to be obtained quickly by using simplified calculation settings. By default, the rough analysis is performed using 50 classes and 8 cross-sections. With a time compression factor of 20%, minor load fluctuations are not taken into account. The 10 nodes with the highest damage sum are written to a file for a subsequent detailed calculation. The preliminary analysis is started. This message indicates that the nodes identified as causing the most damage will be used for the subsequent detailed calculation. The preliminary analysis is now complete. The list of the 10 most damaged nodes generated during the preliminary analysis has been automatically entered. The precise calculation will now be carried out. The calculation parameters will now be displayed to illustrate the difference from the preliminary analysis. The elementary form of the SN curve also yields damage sums for stresses below the fatigue strength. The load history is now divided into 100 classes. For each node, 20 cross-sections are used, in each of which the damage is determined. As we are only calculating 10 nodes, only 10 result files can be saved in this case. We are performing the calculation without time compression. We start the calculation. We obtain a damage sum of less than 1. The component would therefore withstand the load. The size of the output file is limited here to 100,000 steps. If necessary, the limit for the output file could be set higher. However, the life calculation is complete and covers the entire load history. We can view the result in the viewer. We had previously specified the geometry file. We can therefore see the total damage for the few calculated nodes. As an alternative to importing the LST stress files, this section will explain how to import OP2 result files. To do this, the FE interface is configured as shown. We examine the load histories that have been imported. We then go to the FE data, select the geometry file as before, and choose the OP2 file. The load cases have been automatically numbered and correspond to the associated load histories. The FE force of 100 newtons used is specified. For the sake of simplicity, we will continue to use the node list entered below. We start the fatigue life calculation. The result appears with the damage sum. We can now select any node from the node list and view the results. Let's choose node 1078, which was calculated assuming the plane stress condition a plate. Here, then, is the report with many details of the calculation. The results are shown at the end of the report. Let's display a few other results for this node. Here is the range mean pair count. Now we select the rainflow matrices as a graphical representation. Next is the equivalent stress curve, which here is the von Mises stress. The representation of the principal stress angle is used in multiaxial applications. This is because multiaxial problems are characterized by rotating principal stresses. However, in the present case, the set of points is arranged almost vertically, which indicates a nearly uniaxial problem. The maximum principal stress, as indicated by the principal stress ratio, also shows that the degree of multiaxiality is low here. This is because the points are arranged one above the other. Now let us examine the model with the results in the viewer.